Hello students, welcome to PH107 Quantum Physics and Applications. Today I am going to continue our discussion about wave packet and its properties such as phase velocity and group velocity. Part of this we have discussed in the previous lecture. So let's first recap what we have learned so far. So the first thing we have learned in the previous lecture that if we add waves with a continuous distribution of wavelengths, we get a true wave packet that is finite over a limited range in space. So this is a particle of mass m moving with velocity v0 along x-axis, and this is a wave packet. That's what we have seen in the previous lecture, and this wave packet has a slowly varying envelope, and inside these waves are oscillating. These waves are of non-sinusoidal nature, and the envelope, or let's say the wave packet, is moving with velocity vg, which is a group velocity. That's what we have discussed, and here is the definition that we have learned, that the group velocity is written as d omega by dk, whereas the phase velocity is written as omega over k. Okay, so now we can ask one important question based on our previous knowledge, that if electron is going to behave like a wave and there is a wavelength associated with this wave corresponding to an electron, that is Debye wavelength, so how this wavelength and this so-called a wave corresponding to an electron is going to behave, and what is going to be its phase velocity, group velocity, and so on. Okay, so let's recap from previous lecture what we have learned, that the mass is written in terms of the rest mass m0 times this gamma, where gamma is this prefactor, and the momentum is written in terms of gamma as m0 v, and the total energy of an object with this momentum p and this rest mass m0 is written as E is equal to square root of p square c square plus m0 square c power 4, which is equivalent to the mc square, or m is equal to gamma m0. Okay, and we also know from the previous slide that your group velocity and phase velocities are given in this following fashion. Okay, so let's try to compute the group velocity and phase velocity for a particle which has this particular energy, momentum, and mass. Okay, and we know that the momentum p is your h over lambda. Okay, this is what we have seen. So let's see what we are going to learn. So this is our wavelength, and this wavelength is written as h over p. This is our, in some sense, a Debye wavelength, or this can be also written as h over mb. Now the phase velocity we know is omega over k. Now omega is your 2 pi nu and k is your 2 pi over lambda. So total we can write down 2 pi get cancel it out. So the Vp is lambda times v. Now lambda we know, lambda times nu. So lambda we know, now let's calculate the nu. So we know energy is your h nu. Okay, so nu is equal to E over h, and your E is your mc square. Here m is the total mass, not the rest mass, divided by h. Okay, so now we know this value. Okay, so now we can try to substitute this value of nu here and this value of lambda here. Okay, so h get cancel it out, get cancel it out. So what you are going to get? You are going to get c square divided by v. So your phase velocity is written as c square over v, and it is clear that your Vp is much larger than your c square. Okay, because your velocity is much smaller than c for a particle like an electron. Okay, this contradicts our notion that your phase velocity is much larger than the speed of your light. Okay, so what it means, what it signifies? It signifies that the Debye wave associated with the particle would leave the particle behind, because your phase velocity is larger than the speed of your light. So it means that particle will be left behind and the wave will move forward. This is again the wave concept. Okay, that's what we have seen, that the wave packet and inside the wave oscillations goes together. So this is again the wave concept of the particle. So it means that the true velocity of a particle cannot be the phase velocity in this case. Okay, so now let's compute instead of phase velocity group velocity. So this is what we have seen from the previous slide. Okay, and we have also seen this lambda is written as your h over mb. So now we can calculate your omega, angular frequency, as 2 pi nu. Nu I know this, so I can substitute, and now m I have substituted as gamma m naught. Okay, so this is my omega, and I also know my k as 2 pi over lambda, and here what I did, I just replaced the value of lambda from the top to here, so it is written as, and now I again written m in terms of the gamma m naught. Okay, now I also know the definition of gamma, or the value of gamma is written this one. Okay, so now let me write down my group velocity. Group velocity is d omega over dk. Okay, now what I can do, just to make the things in a straightforward way, I can divide dv here and I can divide dv here. So this is something similar to chain rule. So what you got, you written vg as d omega by db divided by dk over dv. Okay, so let's compute first dk over dv, and then we can also compute d omega by db. So d omega by db, okay, so this is your omega, and now you substitute the value of gamma here. So now this omega will depend on v. Okay, so d omega by db can be written as this you can verify, it's just a simple differentiation, and your dk over db is also written as, because your k also depends on your v by a gamma. Okay, so now this factor and this factor is common, so when you take the ratio, so this gets cancelled out, and now 2 pi is also common, and m naught is also common. So what you have got at the end of the day, that your vg is equal to v. So what it signifies? It signifies that the Debye wave group associated with a moving body travels with the same velocity as that of a body. So this is an important concept that we have learned, that if you have a wave, the Debye wave group, which is associated with a moving object or moving particle, then it means that the velocity of this Debye wave is same as the velocity of, or the group velocity of this wave or Debye wave is same as the velocity of the body. Not in terms of the phase velocity, but it is equivalent to the group velocity. Okay. So now let's try to establish a relation between the phase velocity and group velocity and try to understand some more properties about the system. Okay, so let's see what we have learned till now. So Debye wave group associated with a moving body travels with the same velocity as the body. That's what we have seen in the previous slide. Okay, so this is the picture now. It's moving with v0. It means that the associated wave packet will also move with this velocity v0, which will be the same as the group velocity of the wave packet, and that's what we are seeing this picture over and over. So this is the main conclusion that we have made right now. Okay, so now in general, many waves having a continuous distribution of wavelengths must be added to form a packet or wave packet. This wave packet is finite over a limited range in space and really zero elsewhere. Okay, and when you get this thing, in this case your Vg or the group velocity is d omega by dk, and if you have a many waves or wave numbers, then you have to evaluate this quantity at the center, at the mean value of your wave number k0. Okay, so now where the derivative is to be evaluated at the center k0. Okay, so now we are going to set up a relationship between Vp and Vg. So here is your Vg and here is your Vp. Okay, and we can substitute the value of omega as Vp times k. This we have seen in the previous lecture, and now we can perform this product of the differentiation. So first time you will get Vp, another time you will get k times dVp over dk at k0. Okay, now we try to write down, instead of k, we try to write down in terms of the lambda. Okay, we know that k is equal to your 2 pi over lambda. So now let's evaluate this quantity k dVp over dk. So now I can divide d lambda here, I can divide d lambda here as a chain rule, and now I can perform this integral from here. Okay, so what I got, if you do everything correctly, so now k dvp over dk, you have got minus times lambda dvp over d lambda. Now I can substitute this value here. So this is the relation between vp and vg I got in terms of the lambda as well as in terms of the k. Now once you have in terms of the lambda, it is going to give some important insight about the system. Okay, so these are the two relations that we have got it. And now what I'm going to say that if your dvp over dk or dvp over d lambda is 0, it means that if your phase velocity is constant with respect to the wavelength or wave number, then your group velocity and the phase velocity are the same quantity. Okay, so that's what I have shown, that let's say if you have a vp is equal to omega by k, so now if you take this derivative, okay, so you will get this one, and that's what it signifies, that your group velocity or velocity is same here. So this is a simple method, and now we are going to learn more in the next slide. Okay, so if your phase velocity is not changing with respect to k, in that case your vp and vg are the same quantity, then we can say that the medium is non-dispersive medium. Okay, it means that the all component waves have the same speed. Okay, for example, light in a medium with a constant dielectric or constant refractive index. Okay, so let's say this is the dispersion relation we have seen in the previous lecture. So your omega in the case of light is written as kc, where c is the speed of light and n is the refractive index of the medium. Okay, so now you take d omega divided by dk. In this case it will be c over n, and this is your velocity. Okay, and now you can also take omega by k, which is the same quantity you will get. So you see that in this particular case, when light is in medium with a constant refractive index, your d omega by dk and omega by k are the same quantity. So you are indeed going to get a non-dispersive thing. Okay, now let's see when the medium becomes dispersive. Okay, so here is the definition of a dispersive medium. So these are the things that you have seen. So of course, a dispersive medium means that dvp over dk is non-zero. It means that your group velocity and phase velocity are not the same. They are different. They are different from each other. Okay, so it means that the dispersive occurs when phase velocity depends on the k or lambda. Okay, and now we can define two kinds of dispersion. One is the normal dispersion, where your dvp over d lambda is greater than 0. It means that your phase velocity is larger than the group velocity. So you can see that the red arrow represent the velocity of individual waves, where the green arrow represent the velocity of your wave packet or the envelope of your wave packet, and red is moving ahead than the blue. Now instead of normal, the anomalous dispersion is defined in an other way around. It means that your dvp over d lambda is a negative quantity. In that case, your group velocity will be larger than the phase velocity, and the situation reverses. Okay, so this is how you have learned about the dispersion nature or dispersive nature of a medium based on the group velocity and phase velocity and their relations. Okay, and everything you see that originate from the concept of the wave packet. Okay, so before we go into detail and learn something more about momentum, wave vector, and the spatial localization of a particle or a wave, first let's read this question which you're supposed to answer. So consider an electromagnetic wave of the form A, which is amplitude, exponential I kx minus omega t. Its speed in free space is given by c, which is omega by k, and we have seen this speed is also 1 over square root of epsilon naught mu naught. This is what we have discussed in the first lecture. That's what Maxwell has obtained, where epsilon is the electric permittivity and mu is the magnetic permeability of the free space. Okay, so the question is, consider waves with omega is equal to 3 times omega p. Omega p is your plasma frequency. Find the phase and the group velocity of the waves. What is the product of the group and the phase velocity? So this is the definition. This is the question that you need to answer. Okay. So now what we have seen so far, that there is a particle which is localized in space, and let's say if you consider a one-dimensional system, so it is localized on x along the x-axis, and the equivalent picture that you have built for a particle behaving like a wave in terms of the wave packet, and wave packet is an adequate representation of a wave particle duality. Okay, so it means that you are trying to connect spatial quantity like x, y, g in terms of the wave vectors or wavelength and so on, how they are related, and they have a very deep implication in quantum physics. To understand this, let's introduce some more concepts and then we will come to the main conclusion, hopefully at the end of today's lecture. Okay, so let's first consider a periodic function. What is the meaning of the periodic function? So let's say there is a function f of x which is the same as if you uh, uh, let's say shift this x by some value 2l, where 2l is the periodicity of this function. Okay, so let's see how this looks like. So here is a periodic function. You see that this rectangle or step size shape is repeating after a certain interval. Okay, or the other periodic function can be seen like this. So you could see this is some kind of wave, and then after this point it start repeating itself, then after this point it start repeating itself. So it means that when any structure becomes repetitive, it means that the function becomes a periodic function. You have also seen, for example, sine, cosine, all the trigonometric functions are periodic in nature, but these two functions which I have presented in this particular slides are not sinusoidal functions. So these are the periodic but non-sinusoidal waves or functions. Okay, now here is a very important uh, message or the conclusion that Fourier has given. Okay, so what is he said, which is known as a Fourier series. So he said that let's take a periodic function f of x. Okay, this f of x or any periodic function can be written as a superposition of sinusoidal functions. How? So he has given a mathematical form. So let's say if we have a function f of x is equal to f of x plus 2l, where the period of this function is 2l, then this function f of x is written in terms of the superposition of sine and cosine as this following form. So f of x is equal to a naught plus summation over n, where n ranges from 1 to infinity, an times cosine n pi over l times x plus bn sine n pi over l times x, where a0, an and bn are constants and l is related with the period of your function. And this is what is called a Fourier series. So you take any function, whatever shape it is, the only condition right now we are imposing that this function must be a periodic in nature. We will come to a periodic function in a moment, but any periodic function can be expressed in this Fourier series. Okay, and the first question you can ask, how to estimate what is a naught, a and bn, and how these are independent quantities. Okay, so let's do it. Okay, so before that, let's conclude. We are superimposing sinusoidal waves of different wave numbers or wavelength. You see that once the n changes, so this is what is equivalent to the wave length or wave number, and this is what you have seen in case of wave packet. So when you superimpose different sinusoidal waves with different wavelength or wave numbers, you try to form some kind of wave packet. That's what we are trying to come in this class. Okay, so this is the Fourier series, and if you try to estimate a naught, an or bn, then these are called Fourier coefficient. And now I hope by now you have guessed it how to get it. So if you perform the integration of this function from minus L to L, this term both cancel it out. So what you will get this side minus L to L f of x dx. Here this is a constant, and when you perform you will get 2L. You change this to L, so a naught is given in this following form. Now you can multiply this function by cosine of this quantity. So this will give you an, and this term will be 0, and the same way you can write down the Pn. So these are the way that you have to estimate your three Fourier coefficients a0, an, and Pn. Okay, and the mathematics you can verify. So let's say this is a sum function which is a periodic in nature, and this behaves like a step function. So it is 1, then it suddenly dropped to -1. This is a minus sign here. Then again after some time it rises and goes to 1, -1, 1, -1, 1, -1 in a very sharp jump. Okay, and now you may ask how this function can be represented using the Fourier series, what I have shown in a moment. Okay, so here is the result. Of course you cannot do it by hand, so this is done numerically in a computer. So if you add only one component, let's say k is equal to 1 or n is equal to 1, here is the definition. Okay, so I'm putting the value here. So okay, it looks pretty much sinusoidal. Now instead of 1, if you add 5 terms, then you start seeing some kind of steps. If you keep adding 11, and if you add, let's say, almost 49, then you start mimicking almost like this step function. So here is a proof that indeed any periodic function can be represented in terms of the Fourier series. The only question is that what is the value of k you need to choose so that you can represent this in a satisfactory way. Okay, and in this particular case it turns out that your a0 is 0. So here is another way to look this thing. So here are the waves. So first you look these blue colors, which are the waves. So you see this is the first wave with some frequency or wavelength, then this is another wave, then another wave, and then another wave. So you have added so many waves with different amplitudes. So this side you project the amplitude. So the first one is the maximum, then the amplitudes are declining. Okay, and if you look in terms of the Fourier series as the representation of the total function, you see that it looks like more like a stepsize function. Of course here is the oscillation because you have only added a few waves. If you include more and more waves, it becomes more like a constant line, except some wiggles at the corners or edges. Okay, so now let's ask, what about the non-periodic functions? Okay, so can we express them as a superposition of sinusoidal wave? Indeed yes. Okay, so if we can find a way to express our non-periodic function in terms of the Fourier series, then this will help us to solve our problem of a wave packet. A wave packet is localized in space, and this wave packet is not a periodic function like what we have seen just now. Okay, so this is a non-periodic function because this is only once it is happening. Okay, or this is another non-periodic function. We will come to these functions, what they call in detail in today's lecture and later on also. Okay, so how you could think of a non-periodic function is equivalent to the periodic function. So it is the same as imagining a periodic function with length L is equal to infinite. So you could think of that if your function is repeating after certain interval, instead of that you say that okay, I have only one function, the same periodic function, but its length is infinite. Okay, so L tends to infinity. This is the way you can try to think of a non-periodic function in terms of the periodic function. Okay, so as I said that a non-periodic function can be imagined as a periodic function with L is equal to infinity. This is your Fourier series, what you have seen in the case of periodic function. Now this Fourier series can be written in a modified form when L goes to infinity. Okay, so what it means that this integral, this summation will turn out as a another form. So what you have done, so instead of this particular value, what I can say, I can have set this as a kn. Okay, And now this quantity, so n pi over L I have replaced because this is n dependent quantity, n is your running index. So this quantity I called Kn. Now this quantity, when your L goes to infinity, is replaced by integral. So whenever your discretization becomes infinite, it's obvious in physics or mathematics that the summation has to be replaced by the integral. And in this following fashion, what you can do, you can write down this an as ak, it become a function of k, and this cosine kx and bk sine kx, and then this summation is turned out to be integral, and we have dropped out a0, or you could say that the a0 has been um, a compensated with an and bn, and that's why we have a new definition of ak and bk. Okay, we notice that now we are considering a continuous distribution of wave numbers, so not any more discrete 1 to 5, 1 to 10, or 1 to infinite, but it is a continuous for different constituent sinusoidal wave. Okay, so now we can, instead of Fourier coefficients, now we can talk about the Fourier component. So similarly, we can write down ak as 1 over pi minus infinite to infinite fx, which was the function, times cosine kx dx, and the same way we can write down the bk. That you can verify, as we have seen in case of a0, a and bn. The same way we can write down the ak and bk. Okay, now this cosine and sine can be written in terms of the exponentials, e to the power ikx plus e to the power minus ikx divided by 2. This is the definition of your cosine. I hope you have seen in your 10 plus 2 level. And this is the definition of your sine. So once you substitute it, and then you collect different ak's and bk's combinations and say, okay, this is my only terms of e to the power ikx, and there is another term of e to the power minus ikx, then everything will simplify, and finally we can write down f of x as integral over g of k, okay, e to the power ikx dk, and this is your normalization constant. Okay, so there are some simple mathematical steps involved that you can do it by yourself. And now I can inverse the Fourier, this transform, this Fourier integral, and I can write down my gk as 1 over square root of 2 pi, and instead of ikx I will get minus ikx. So these are relation that is coming out from here. Okay, and these are going to now build a new concept in quantum physics, which is a very important and has a very deep implication in quantum physics that we will see in coming lectures. Okay, so now once we are able to express any non-periodic or aperiodic functions in terms of the Fourier series or Fourier integrals, then it is easy to visualize the wave packet in terms of these numbers. So how we are going to visualize the wave packet? So let's say this is the definition that what we have seen, and now these components have a meaning in terms of the wave packet. So the first, let's say this is your wave packet, a resultant wave packet. So what it means, this becomes like a constituents of the wave packet, or these are the waves. Okay, so this is the amplitude of your constituents wave, because this is your plane wave e to the power ikx, and this is the component which we call as a high frequency constituent plane waves. Okay, so this is how we can visualize, or we can see the wave packet in terms of this Fourier integral. Okay, so let's do the first example and see what we are going to learn, and this will set a stage for next class. Okay, so let's say a function g of k is 1 when your k is ranging between k naught minus delta k by 2 to k naught plus delta k by 2. So in this small range your function is 1, otherwise it is a 0. So you could immediately see how this function looks like. So this function looks like this. Okay, so these are the range where this is non-zero, this is non-zero, and then otherwise it's a 0. Okay, now let's estimate what is your f of x. Okay, so this is the expression that we have learned, that f of x is related to g of k. Of course your g of k is non-zero in a given interval, so your limit will be replaced from minus infinite to plus infinite by k0 minus delta k by 2 to k0 plus delta k by 2, and then gk becomes 1, and then it remains 1. Now you could perform this integral by yourself. It is pretty trivial, and this is the resultant that you are going to get. Okay. Okay, so that step you can verify by yourself. Now let's plot this and how this looks like. Okay, so what we are going to do, if you notice there in this one, so this component is complex signature because here you have e to the power I k0x. So this is complex in number. So we cannot plot complex number at this stage. So what we are going to do, we are going to look only the real part of this thing. Okay. So if you take the real part of this thing, so e to the power I k0x will give you the cosine k0x. This is the real part of this exponential, and rest of the things remains as it is. Now if you plot this quantity, okay, now can you see something that you have learned in the previous lecture? This looks pretty much like a web packet. Okay, so width of the web packet is given by minus 2 pi over delta k to 2 pi over delta k. So the width of the web packet is 4 pi over delta k. Okay, the inside components are this cosine k0x, and this envelope is given by this quantity. Okay, so that's what I have said. Okay, now what happened when you change the value of delta k? Okay, that's what we were trying to learn in the previous lecture, that okay, you fix the mean value k0 and you can increase or decrease the number of waves by adjusting the range. So here what we are saying that okay, let's change the value of k0 in your problem. So what we did, so this is the expression that we have seen in the previous slide. Now what I did, so you see this was my original box, which was the solid line, and now what I did, I just increased the value. Okay, so this dotted line is now my increased value of this box. Once I have increased the value, how this will affect to my this quantity? Okay, because this quantity depends on your delta k. Okay, and we have said that the width of your web packet in the previous slide, let's go back, your spatial extent depends on reciprocal of delta k. Okay, so if you increase delta k, what will happen? Your spatial extent will shrink. Okay, so this was the thing that we have seen. Now what will happen when your delta k is increased? The extent will shrink, and once it shrink, the amplitude will increase. So this f of x will increase. Okay, so now you could start thinking that the k or delta k, whatever you want to say at this point, is related to the spatial extent of the wave packet, and they are not the independent quantities. Okay, so there is some kind of conditional relation between the two variables or two quantities. Okay, so we will continue this in the coming classes, but before I end today's lecture, let me provide the recommended readings. That if you want to read wave groups and dispersion further, which was the half of the topic of today's lecture, please go back to section 5.3 in this book by Survey and co-authors. And if you want to read about Fourier integral, please go to section 5.4. Okay, thank you very much and see you in the next class.